Good morning, everyone, and thanks so much to the organizers for inviting me. It's a real pleasure to be at NUS and in Singapore for the first time. What an amazing city. I'm going to talk to you today about finding bugs in compilers, and I'm going to give you a bit of an overview of the field of randomized compiler testing, and I'm also going to talk to you a bit about some of my work in that field, and I'll say a little bit about Graphics Fuzz, the startup company that Ilya mentioned, not so much talking about the company, but talking about the technology that we created. I hope I don't need to convince any of you here that compilers need to be reliable. If we don't have reliable compilers, then we can have the problem where we've got a correct program, maybe even a formally verified program in source code that then gets compiled then to an executable that is incorrect because of a bug in the compiler, which could lead to the executable behaving unexpectedly at runtime, maybe undermining the guarantees of formal verification if the application was formally verified. And I thought before going into the details, just for a bit of fun, I would start by waking you up with a couple of examples of compiler bugs in practice. So the first compiler bug I want to show you affects the JetBrains Kotlin compiler. I'm going to go to the IDEA IDE here. Hopefully this is large enough for you to see at the back. Now, in the Kotlin programming language, which is kind of like a much better version of Java, the language has a lot of nice features. One feature that isn't so nice is that you can compare Booleans. Why would you want to compare Booleans? But anyway, you can. And true is greater than false. So I wonder, could someone tell me what should this program print? True, okay? So let's try running the program and see if it prints true. And, well, you can see I ran in advance, and indeed, it does print true. We run this program, and we get true printed. And what I'm going to do is just take this occurrence of true here, and I'm going to rename it temp. And I'm going to declare val temp of type Boolean equals true. Okay? And evidently, the program should still compile successfully and print true. All right. What if we instead make this true be 2 not equal to 1? I think you'd all agree that 2 not equal to 1 is true. And now I run the program, and it prints the value true. We're getting some warnings from the IDE here telling us things like, that expression is guaranteed to evaluate to true. What are you doing? But anyway, a legitimate program. And now we might think, well, you know, if we can use 2 not equal 1 here, then why don't we grab that expression and just replace temp with 2 not equal to 1? And now what we find is that the compiler is saying expected a comma or a closed parentheses. So the compiler is now refusing to compile the program, right? So this is a bug in the front end of the compiler where the compiler is failing to accept a legitimate program. This program is completely valid Kotlin. It's a bit of a strange thing to write, but there's absolutely nothing wrong with writing it, but the compiler is rejecting it. Okay? This kind of compiler bug is not very serious because you know about it as a software developer. Ahead of time, you know this bug exists, and you're not going to end up deploying incorrect software because of this bug. Or at least that's the case for languages that are compiled ahead of time. I do a lot of work in the world of GPU computing, graphics computing, where I mean proper graphics, shaders, things like OpenGL, Vulkan, HLSL. And in that world, you actually have the notion of compilers being compiled, shaders being compiled at runtime. If you ship a computer game, for example, the computer game will ship with a whole load of shaders that come as source code, and when you load the game, those shaders get compiled for the GPU that's in your system. And if compilation fails, the game won't run. So actually, these kind of ahead-of-time bugs sometimes can be important even in terms of making an application work when it's deployed versus not work. Anyway, in Kotlin, that's not the case. So this is a kind of fun but not terribly serious bug in Kotlin. I thought I might then just show you an example of a miscompilation bug where a program is merrily compiled by the compiler, but the resulting binary just does the wrong thing when you run it. So let me go to VS Code. And this program here, bug.c, is a bit of a strange looking program, but actually it's very easy to understand what this program should do. If you look, we've got this function at the bottom, int main, and what main does is it prints array D at index 0, right? It doesn't call any other functions. It just calls printf with array D index 0 as an argument. Now, where is array D declared? Well, you can see it's declared at line 3 of the program. We've got a static short array D of length 1. And in C, a global variable is initialized to 0 by default, all zeros. So unambiguously, this program, when we compile and run it, should print 0. You don't need to even look at the function h or the function e, because those functions are not called. So it doesn't matter what they contain. As long as they're syntactically correct and don't block compilation, doesn't matter what they contain, this program should print the value 0. Agreed? Yeah? So let's use the good old Windows subsystem for Linux here. And let's compile the program with GCC 11. And we will, with Clang 12, the Clang compiler. So compile bug.c. And we get a warning about incompatible pointer types. Okay? This is just a warning, it's not an error. And this warning is related to the function h, which, as we discussed, doesn't matter because this function is not going to be executed when we run the program. So let's run the program. And indeed, we get the result 0. Okay. So now let's compile the program again. But this time, let's enable optimizations. Let's do O2. We get the warning again. And now we run the program. And this time, we get a floating point exception, which is typically what you get when you do, as it happens, in integer division by 0. For some reason, on x86 platforms, you get a floating point exception. So the point is that this perfectly legitimate program, when we compiled it with optimizations, has crashed. This is a bug that was found by us at Imperial in the C. Smith Edge project, which was a collaboration with my colleague Christian Kadar, who's visiting NUS at the moment, and our then postdoc Karine Even Mendoza. And when we reported this to the Clang folks, we got some kind of interesting discussion with them where they were saying something like, basically D0 becomes, for reasons I don't grasp right now, and then this confusing thing here. It looks like the compiler has known that D0 is going to be a select between 0 and the only other value that's written to D0 anywhere else in the program. So for some reason, the value that's going to be written indirectly into D0 on line 12 somehow gets mixed up with this access of D0 in main, right? So even though this is a completely different function, a compiler optimization is leading to some sort of interplay between the code in main and the code in that other function, and there was a bug in the compiler that meant this code was miscompiled. Okay? So just a nice little example of a miscompilation bug. And bugs like this can be devastating because they can be compiler version dependent, they can be optimization dependent, they're quite hard to defend against. And in this talk, we're going to look at various techniques for finding these kinds of compiler bugs proactively. Before I get going, then, any questions on those little programs I showed you? Anything else you'd like me to try while I'm in demo mode? Yeah? Does it happen O1? Oh, let's see. I think so, yeah. No, it doesn't happen at O1. So O2 or O3, yeah, but not O1. And it doesn't happen in the latest version of Clang. Okay, this has been fixed. And actually, when I was trying to find some compiler bugs to demo to you, we found lots of nice bugs in GCC in that project, some more critical bugs than this one. But the problem with GCC is that the developers are really rigorous and they backport fixes for critical bugs to many previous GCC versions. So all of the GCC versions I could get on my Windows machine all had the bugs fixed, so I couldn't demo them to you. But luckily, the Clang developers are not so rigorous. Okay.
I find the second example more convincing than the first one.
Absolutely, right? So, yeah.
Write programs like false less than true,
Yeah.
Is there any study on like how much of the compiler fuzzing is solving this kind of esoteric bugs like the first example versus the second one? I understand this is a little bit hard to do because you have to define esoteric.
Yeah, it's challenging. I'm going to talk later on in the presentation about a study on the impact of fuzzer-found bugs versus real-world compiler bugs, which will go some way towards answering that question. But in general, no, it's very difficult to know when bugs matter. And when I was working at Google on compiler validation, we would sometimes have this satisfying finding that our fuzzer had found a bug, that no one fixed. And then later that bug would affect a game. These were graphics compiler bugs. And suddenly it would be all hands on deck, let's get this bug fixed. And what was satisfying but frustrating about that is that's the only way you get feedback that your fuzzing matters, when people don't fix your bugs and then it shows they should have. It turns out they should have done. But of course that defeats the point of proactive bug finding, right? Ideally with proactive bug finding, people fix the bugs and you never know whether they needed to. So a little bit like defending against terrorism, right? You do all these things and you don't have a terrorist attack and you have no idea whether that's because of your mitigations or just because you were lucky. All right?
One point about human written code is that machine generated code don't need to look anything like human written code.
Yes, that's a very good point, right? So we do often have compilers that generate code in lower level languages that get compiled. So we sometimes do get pretty strange looking code that no human would ever write. Maybe there'd be an expression that is trivially constant foldable and a human would never write it, but because a deterministic program has emitted it, it just comes out in the wash. Okay. Yeah, sure.
After you report the bugs to them, they fix the bug.
Yeah.
So
Not the Kotlin one. Yeah.
why they don't fix the bug?
That Kotlin one, I have no idea why they don't fix the bug. I think the Kotlin...
Whether their team is not no power.
It can be due to developer priorities, developers being overwhelmed, knowing they've got a rewrite of the compiler that's happening already and there's no point fixing bugs in the compiler version that's about to be retired. It's a whole interesting, not with respect to compilers, but generally attitudes towards fixing bugs, especially bugs found via proactive testing. That's a really interesting area that I think would be good for a kind of social study.
The software has a new release, update some sort of bugs, or they fix some bugs. So they should fix that.
I didn't understand your question, but essentially the bugs that tend to get fixed very rapidly are the miscompilation bugs, cases where the compiler produces semantically non-equivalent code. Those bugs people tend to be very hot on fixing. Cases where the compiler rejects a valid program but a weird program, people tend to not be so bothered about fixing those. And to me that makes sense. Right? Those bugs, like the Kotlin one I showed you, is this really a big deal? I don't think so. It's kind of fun to show the students when I teach Kotlin. Okay. So before I talk about compiler testing, I just want to give a nod to the fields of compiler verification and translation validation. You may have heard of CompCert, which is a really amazing project on building a verified compiler for a subset of the C programming language. Here, the compiler is formally verified so that any program it agrees to compile will lead to generated code that has semantics matching the semantics of the source program. Translation validation is something a bit weaker than compiler verification, where instead of verifying the compiler in its entirety, you have a compiler that can emit object code plus a proof of correctness that that particular compilation preserved the semantics of the source program, typically a proof that can be independently checked. And there's been a successful example of translation validation applied to the LLVM compiler, components of the LLVM compiler, via the Alive2 project. And these approaches are very interesting, and I hope there will be much more work on these areas in the future, but they suffer from some problems. First of all, most compilers for major programming languages aren't correct. So compiler verification is not really on the table. You can't verify something that is not correct. You may try to verify it and provide tremendous value by weeding out many bugs and semantic problems, but you can't verify it if it isn't correct. And the second thing is that most real-world programming languages don't have formal semantics. And as I'll show you in a moment, some of these languages can't have rigorous formal semantics. As someone who comes from a formal methods background, I hate to say that, but as I'll show you, it's true. Some languages are never going to have rigorous formal semantics because they can't, in which case doing verification of the compiler is completely off the table, and testing is the best that you can do. So the focus of the rest of my talk is going to be about compiler testing, trying to proactively find bugs in compilers so that they can be fixed ahead of time if the developers deem it worthwhile to fix them, and try to make the lives of end users better. So try to make sure we get these bugs fixed before they affect end users. And an appealing idea for testing compilers is to use randomized testing, also known as fuzzing. And a way we might consider doing this is to build, for the programming language we care about, a generator of programs, and then invoke that generator repeatedly to produce a stream of generated programs, push each program through the compiler, execute the resulting binary, and then look at its result to see whether that result is correct. But what's the obvious problem with that approach? Anyone?
We don't know the answer also.
Exactly, we don't know the answer, right? We don't know what the result of running this randomly generated program should be. So if we get some result, how do we know whether this result is the result we expected to see? Okay, this is known as the oracle problem. The oracle problem is a major problem in software testing in general, and it is a challenge when you test compilers in particular. So let me illustrate the oracle problem to you in the context of GPU programming, and I'll come back to this point about some languages not having, even in principle, a formal semantics. Here I've got a little piece of OpenGL shader code. In the world of GPU computing, a shader is a program that is going to run on the GPU. If you've done general purpose GPU computing, you might have written CUDA kernels or OpenCL kernels. Well, shaders are the graphics version of those kernels. So you don't need to look at this code other than to see that it's a non-trivial piece of code. It's using a load of vectors and floating point numbers. And ultimately, this code is going to produce a pretty frame. Okay? So if we would run this and grab a frame of the animation that it ends up producing, then we might get this nice picture here. In fact, this is the picture that I got when I ran this program some years ago on a GPU and captured a frame. So the question might be, should it produce this frame? Is this the right answer for that program to have produced? Right? Should we get this picture? Well, how would we check this? How long would it take to find out if this is the right frame? Maybe we could hand execute the program for every possible pixel and check that we get the right color value. That would take a very long time. And does the question even have a clear-cut answer? In other words, does there exist an oracle for this problem? Is there a way of knowing whether that image is exactly the image you should get when you run that graphic shader through the graphics pipeline and grab a frame? Yeah, Umar. Yes, that's a good point. So the point was, if you find a discrepancy, when you're doing compiler testing, say you do somehow know what the end result should be and you find that you get a different result, do you know that's the compiler's fault? What if you're calling libraries? Could it be bugs in libraries? Could it be a hardware bug? Absolutely, it could be, right? So this is black box testing, and we're treating the compiler and everything it uses and everything underneath it as a black box. And in principle, it's possible we might find bugs in libraries or in hardware. Okay? And in my work on GPU testing, informally, some GPU developers told us that some of the bugs we reported did turn out to relate to hardware bugs. But we never got insight into that because these were closed source systems. But the vast majority of the time, they were bugs in the compiler. But yes, it's a good point.
So that bit has to be decided manually.
That bit would have to be decided manually, yes. Whenever you do black box testing, you have this issue that when something goes wrong in the black box, you have to then do some detective work if you want to work out where in the black box it's gone wrong. Okay, so going back to this example, should we get this image? Well, actually, in this case, there's no right answer because OpenGL is a really, really horrible language. The OpenGL shading language specification has this text. It says, and this is with respect to floating point numbers, any denormalized value, that's a floating point number really close to 0, can be flushed to 0. The rounding mode, that would be round towards infinity, round towards nearest even, there are various floating point rounding modes. The rounding mode cannot be set and is undefined, meaning it will be one of the IEEE rounding modes, but you can't say which one you want. It will just be whatever this particular GPU uses. Notta numbers are not required to be generated. So what that means is if you do something like 0 divided by 0, you might get a Notta number, but you might just get some other value instead. And then, unless you use something called precision qualifiers, implementations are permitted to perform such optimizations that effectively modify the order or number of operations used to evaluate an expression. And then I love this text in blue as a formal methods person, even if those optimizations may produce slightly different results relative to unoptimized code. So you've got a language specification that is more or less saying, as long as it looks right, it'll do. Right? An explosion should look like an explosion. A falling tree should, make a crashing noise. Okay, no, it's a graphics API, not a sound API. But the point is that this OpenGL API and language was used as an umbrella for a whole load of existing GPU designs and existing GPU compilers. If the language would come along and say, you have to do exactly this with floating point, that might really suit NVIDIA, but be terrible for AMD, or might be really good for ARM's Mali embedded GPU, but terrible for Qualcomm's Adreno GPU. So as a compromise, this umbrella standard has to have very relaxed rules, and there is no way to give a formal semantics to this. There's not even a way to give an over-approximating semantics saying the result you should get should be in this envelope of acceptable behavior. It really is very informal here. But nevertheless, we do have the notion of clear-cut compiler bugs in this domain that we'd like to be able to find. So we want to be able to find bugs in a domain where we're inherently going to be a bit fuzzy. We're never going to have a completely formal semantics. So there's no oracle here. And even when the language is precise, we could build a golden reference compiler for a language, but writing that golden reference would be as hard as implementing a compiler for the language, and there would probably be bugs in our golden reference. So would we be able to trust the golden reference? Probably not, unless we go like the CompSert route and formally verify it, which is a tremendous undertaking. So for large languages, not large language models, but actually large programming languages, it's rare to see a golden reference that truly respects the rigorous semantics of the language, if indeed the language has a rigorous semantics. And this leads to a slight detour into the notion of non-testable programs from a very nice paper by Elaine Wayaker in 1982, when I was 1 year old. So Elaine Wayaker coined the term a non-testable program, saying that a program should be considered non-testable if either of the following hold. One, there does not exist an oracle. This is the case in exploratory software. Say you're trying to write some software to explore some scientific phenomenon, and the whole point is you don't know what this phenomenon is. You're trying to discover it. Well, you can never have an oracle for that kind of software. Or it's theoretically possible, but practically too difficult to construct an oracle for the software you're trying to test. And I would argue that in the domain of compilers for mainstream languages, normally we should consider these compilers to be in the class of non-testable systems in the sense of Wayaker, either because there can't exist an oracle, like in the OpenGL case, where there is not a rigorous semantics, or in the case of something like C++, where the language is huge or fiendishly complicated, and no one is, there aren't that many C++ compilers in the world. Building a golden reference C++ compiler, you're not going to do as good a job as LLVM Clang have done, or as Microsoft have done with their compiler. Your golden reference is very likely to be more buggy than the things you're trying to test. Okay? Any questions at this point about this business of oracles or non-testable programs? I would definitely recommend having a read of this paper. It's a classic. All right. So I'm going to talk about avoiding the oracle to make compiler testing tractable in practice. Then I'm going to talk a little bit about the graphics project that I led at Imperial, which led to a startup company which was acquired by Google, and where we spent some time at Google rolling out the technology. Then I'm going to talk in quite some detail about undefined behavior, which is one of the phenomena that makes compiler testing hard in practice. And I'm going to talk about a special interest of mine, which is test case reduction, where you've find a bug using a large program and you want to have a small program that reproduces the bug, which is quite challenging, especially because of undefined behavior. And then finally, I'll mention this study that I alluded to earlier on the importance of compiler testing in practice. So first up, if you want to do practical compiler testing, a very successful strategy you can resort to is known as differential testing. This is where you need to have either multiple compilers for a programming language that agree on implementation-defined behavior, or you need to have a compiler that can be configured in various different ways, maybe no optimizations versus full optimizations, which you can conceptually think of as two different compilers. So you randomly generate a program using your program generator. You feed this program to the two compilers or compiler configurations at your disposal. They give you executables that you then run to get execution results, and you compare those results. And if the results are not the same, that means you found a bug in the compiler or in the compiler infrastructure, including the libraries and the hardware, right? With me? Would anyone like to dispute this? Is it certainly the case that we're going to find a bug using this technique? Yes, that's a really good point. In the world of GPU computing, it might be that you get different results because of acceptable differences in floating point semantics. So you might need to make this equality be some sort of appropriately fuzzy equality that's going to give you a very high chance of distinguishing between compiler bugs versus just acceptable floating point differences. So that yes, that's indeed one reason why this might not indicate a bug. Yeah. Exactly, right? So if we have a non-deterministic program, then we might legitimately get different results from this. So if we had random generation in the program, so to be clear here, the programs are randomly generated, right? But we need them to be deterministic, as you just pointed out. They can't be programs that use randomization internally. If we want to do differential testing of concurrent programs, the compilation of concurrent programs, then this is not a straightforward technique to apply because concurrent programs can exhibit legitimate non-determinism. All right? And another reason is undefined behavior, which is broadly under the same banner as non-determinism, but you may have features of the programming language that have undefined semantics or that give rise to undefined behavior, in which case you might deterministically get the same result after compiling with one compiler and another result deterministically with another compiler, but different results. And that may be nothing to do with a compiler bug. It may be due to your program triggering undefined behavior that's being resolved in different ways by different compilers. So that's something that also needs to be taken care of here. All right? So it's not as trivial as just naively generating programs and looking for mismatches. And we'll talk later on about some of the nuances to this. And then the other main pseudo-oracle I want to talk to you about is called metamorphic testing. So metamorphic testing is particularly useful when you only have one compiler. Maybe this is a brand new programming language and you've implemented the first compiler and you want to do some testing of it. Or where you've got a compiler that does have lots of implementation-defined behavior. So cross-checking between compilers would be fraught with difficulty because of implementation-defined behavior, but sanity checking one compiler against itself may be more reasonable. So the idea here is that you have some program, maybe a randomly generated program, maybe an existing program, a test case perhaps. And then you have a mutator that can randomly mutate that program to give you another program, which I've indicated by program prime up here. But that program prime is going to be semantically equivalent to the original program. So these mutations can't be arbitrary mutations. They've got to be semantics-preserving mutations. And I'll give some examples of those later on in the talk. If we've got these programs, program and program prime, that are semantically equivalent, if we push them through the same compiler to get executables and run those executables, then we should expect to get the same result because the programs are semantically equivalent. And result mismatches would indicate bugs. But again, this is subject to the program being deterministic and free from undefined behavior, and those mutations that are semantics preserving as part of that not introducing any undefined behavior. They wouldn't be semantics preserving if they did, but nevertheless, it's worth noting they can't introduce undefined behavior. Otherwise, you might get legitimate differences between the execution results for the two compiled versions of the program, and that would not indicate a bug. But broadly, these two approaches, differential testing and metamorphic testing, do they make sense? Any questions about them? Very kind of straightforward, classic pseudo-oracles in software testing. And I should say, these can both be applied to other systems. They're not specific to compilers. The way I've presented them here is compiler-specific. But the idea of cross-checking implementations or cross-checking should-be equivalent results for inputs to a system under test are widely used techniques in industry and in academia. Okay, so this is all made difficult by the horrors of undefined behavior, especially in languages derived from C. So C and C++ and many of these GPU languages I'm interested in. You have things like division by zero, arithmetic overflow for signed numbers, out-of-bounds array accesses that give you meaningless programs. If your program triggers one of these operations, then the program has no semantics for that particular input. And I'm going to talk about this in a bit more detail later on. It's a lot more subtle than I realized before I got interested in this kind of area of computer science. So differential testing requires that generated programs are free from undefined behavior, and metamorphic testing requires that the original program is deterministic, free from undefined behavior, and that the transformations don't poison the program by introducing any such problems. The biggest success story, in my opinion, of differential testing is the C-Smith project from the University of Utah in 2011. It was published at PLDI, and it won a Distinguished Paper Award, a Test of Time Award at PLDI 2021, Most Influential Paper Award. So this is a generator of C programs that are pretty rich and complex and are free from undefined behavior. And in the context of metamorphic testing, in 2014, there was a technique called equivalence modulo inputs testing from, at that time, UC Davis, from Zhendong Su's research group, now based at ETH Zurich. And this is a really successful application of metamorphic testing. And in the context of C compilers, these techniques led to the finding and fixing of a very large number of bugs, many miscompilation bugs. And in the case of LLVM, I think Zhendong Su's group were credited by the LLVM developers, thanking them for all of their bug reports, which, in the words of the developers, substantially improved the quality of the compiler. So these techniques have really had a lot of impact in practice. And I thought just to make things a bit more concrete, I'd just show you an example of a program C-Smith generates, because when I talk about these randomly generated programs, I don't know what you have in your mind, but I'll show you what a C-Smith program looks like. So I'm going to go here, and I'm going to run a command I ran earlier. So I'm going to run, where is it? In fact, let me just do it from here. So I'm going to do, oh dear, C-Smith. Build source C-Smith -o prog.c. Okay, this has generated a program, and let's have a look at the program. So this is a fairly short program, right? We've got a bunch of global variables that have been declared. We've got one function, and that function does some random computation, and then we've got a main that is going to call that function, and then hash together the values of all the globals, and ultimately it's going to print the value of the hash it computed. So that's a pretty small C-Smith generated program. Let's generate another one. You can see that it took a bit longer that time. Now we've got a much larger program, right? So let me just sort of scroll through this program, and you can see how horrible this program is. Right? We've got all of these crazy global variables going on and on and on and on, and then we've got many functions, and these functions are absolutely insane, right? Although you can see that they are idiomatic. While this program has been randomly generated, you can see that it's got an idiomatic structure. It's not sort of a pure random program. It's very much a variation on a theme, right? And this program is, a pretty long program. It goes on and on and on and on. So yeah, a couple of thousand lines, and they can be much larger than that. I just thought it would be worth showing you that to kind of give you an idea of what they look like. And then if I use GCC to compile that program, so if I compile prog.c, I've got to do some includes. I've got to say include temp csmith runtime and temp csmith build runtime. Sorry, I missed a minus I here. So we get many warnings when we compile this program, but when I run the program, then it may not terminate, right? If it doesn't terminate, then we just time out and generate another program and try that one instead. So maybe we had a non-terminating program here. Let me just generate another one. Let me compile it and run it, and here we get a checksum printed, okay? And the idea would be that then we would compile that program instead with another compiler like clang12 at -03 and run that program, and we get the same checksum generated. If we didn't, that would be suspicious. That would indicate that there would be a compiler bug. These days, it's very hard to find bugs in Clang or LLVM with C-Smith. Why do you think that is? Yeah, because C-Smith's been done to death on those compilers. They've become immune to C-Smith because C-Smith has found so many bugs in them, it's very hard to find anymore. Does it mean there are no bugs? No, because we find bugs in them. So the thing about testing is you're only going to find the bugs a given testing tool is capable of finding. And the best thing to do really is to have a variety of different testing approaches and apply as many of them as possible. Yeah. Okay, so that was an example of C-Smith in action. Now I want to tell you a bit about graphics fuzz, which was the metamorphic testing approach that my group designed at Imperial College London, which we then used as a basis for a startup company which was acquired by Google back in 2018, and the three of us moved to Google for some time to deploy the technology there. So the graphics first technique is described in an OOPSLA paper, and then we have an experience report about some of the activities we did at Google deploying this. But the approach is basically very simple. So I apologize for those of you in the room who are computer graphics experts. What I'm going to say is a vast simplification of the truth. But roughly speaking, you can think of a graphics shader, a GPU program, as being fed into a graphics pipeline, which comprises the graphics driver, which is the code that controls the GPU, and then the GPU hardware itself. And inside the graphics driver, there is a shader compiler that is going to compile the input shader program to GPU-specific machine code to run on the device. And ultimately, you're going to get an image displayed on the screen for one frame of the GPU computation. So with graphics fuzz, it's an application of metamorphic testing. What we do is we take this original shader and we apply a large number of semantics-preserving transformations to the shader at random. And we do this many times to get a whole stack of equivalent shader programs. Shader programs where if we run them, we should end up getting the same image rendered. And then we push all of these through the GPU pipeline to get a stack of images out. And what we should find is that all of the images are the same, modulo these small floating point differences, which I won't go into details of how we accounted for that, but we used a fairly simple image comparison metric to avoid false alarms due to acceptable floating point differences. But yeah, if we would get this pretty picture at the top for the original shader, then we should get the same pretty picture for all of the variant shaders. And the nice thing about metamorphic testing is we don't need to know whether that is the right image to be getting. We just know that these semantics-preserving transformations shouldn't have changed the image that we get. And if we find instead that we get, say, a black image for one of the variant shaders, then we know there's a bug somewhere in the graphics pipeline, very likely in the shader compiler. And if we instead find that the shader compiler crashes, or sometimes we found cases where we would get blue screens where we would really cause a device to completely fail, then that's a more critical bug in the shader compiler that's leading to rogue code running on the GPU that's causing some sort of interplay with the OS that's leading to a kernel panic. So this is the basic idea of the graphics fuzz testing approach. And to give you an example of semantics preserving transformations, there are tons of them implemented in the tool, but some pretty simple examples. One is injecting dead code. At any point in the graphics shader, you can write if false and then some arbitrary code, as long as that code is syntactically and type correct. Okay? So this should definitely not change the semantics of the program. And you might assume that a compiler would just eliminate that code. It would see if false, eliminate it. And hopefully it would. That's something that should be tested, not testing whether it does, but testing that it doesn't completely mess up in trying to do so. But we would be fools to always inject such obviously optimizable code into these shaders. So instead we can play tricks, like we can equip the shader with a uniform. This is a constant that is passed in at runtime to the shader. A uniform called f, and then we can say, if f is less than 0, then do this arbitrary code. And the compiler will have no idea what f is going to be at runtime, but when we actually run the shader, we can always pass in the value 1 for the uniform. That way, the compiler's got to compile that code in the injected block. It can't optimize it away. It must compile it in a way that doesn't mess up any of the code elsewhere, right? And if it ends up making mistakes and causing sort of leakage between the code in the if and the code outside, a bit like the example we saw at the beginning where we had that leakage between code in the not called function and code in main, then this may trigger some compiler bugs. As another example, we might take some existing code and wrap it in a loop that does exactly one iteration. Now the mechanics of implementing this are kind of tricky. If that existing code declares variables that are used later on, then we can't do this because those variables would not be in scope because of being now inside the for loop. So there are some subtleties to make this work, but conceptually a very simple transformation. We have some code, doing that once is the same as doing it once, right? Or doing it is the same as doing it once. So we can wrap this inside a loop, and then we could, if we wanted, obfuscate the loop bounds. So we could use some uniforms to make it unclear to the compiler how many times this loop will execute. And we have more complicated ways of obfuscating the transformations we apply here, and we randomize those. So sometimes we will not obfuscate at all, sometimes we'll heavily obfuscate, sometimes there'll be some intermediate obfuscation.
What's uniform?
Sorry?
What's uniform?
Uniform is a value that's passed into a graphics program at runtime, a constant that's passed at runtime. And it's uniform because these programs are executed for every pixel in the image, roughly speaking, and uniform means every pixel instance will get the same value for this constant. All right, one more example then. If we have some scalars and small vectors, we might pack these into a larger vector. So here we've got a floating point number d and a two-dimensional floating point vector v, and one transformation would randomly find these and decide to replace them with a three-dimensional vector. I'm going to call it here dv. It would be called some auto-generated name by the tool. And dv is going to have the values 42, 1, and 0, corresponding to the fact that the floating point number had the value 42 and the vector had the values 1 and 0. And then whenever we would have used either d or the components of v, we now use corresponding components of dv, right? So where we would have used d, we now use dv.x. And where we would have used v, we use either dv.y or dv.z. Okay? So this is just a way of making the code different, so the compiler is going to apply different optimizations. It's got a different task on its hands, but that task should lead to the same outcome. And these transformations can be very effective at triggering compiler bugs in practice. Make sense? Yeah? And quite a fun thing to work on, because you can just sort of wake up one day thinking, oh, wouldn't it be cool if we tried some weird and wonderful transformation, and then it just comes down to how hard is it to implement this inside the program transformation framework as to whether it's worth trying. But you can kind of, within reason, throw anything you like at it and see what bugs fall out the other end. Here's an example of a miscompilation bug. And again, you know, this is raises the question, does this bug matter? But anyway, here's an example of the bug. So we had a shader that would have produced this nice image on the left originally, and this, in my opinion, equally nice image on the right, but an obviously bad image on the right. And the diff is so our tool applied many transformations, but after test case reduction, the transformation that remained, which triggered the bug, replaced a return of a call to default color with a switch statement, switching on the value 0, and if the value of 0 was 0, returning default color. Right? Obviously, a semantics preserving transformation should make no difference, but instead caused something horrible to go wrong. This was black box testing. This was an AMD GPU, if I remember correctly. We don't know what the source of this bug was ultimately, but it was a bug, and they fixed it. Okay? And something I find interesting is you might look at this and think, if you're a purist, you might just think a bug's a bug, this should be fixed. If you're a pragmatist, you might think, well, no one would ever write that, who cares? But of course, this is just the way our automated testing tool managed to trigger this compiler bug. It doesn't mean that you couldn't trigger the same underlying bug in a more natural way. So it's important to think about that when you think about the artificiality or otherwise of bugs, right? Just the way the bug is presented by a given tool doesn't mean that the underlying problem needs such a strange presentation to go wrong. We, along the way, found a number of security bugs using this technique. We found cases where we would just lead, devices would crash or they would render garbage, and sometimes that garbage would have come from places it shouldn't have come from. One of these cases was where we could get an iPhone 5 to render garbage, and it looked like white noise, but we contacted Apple about it and disclosed it to them, and they confirmed that actually this white noise was coming from some out-of-bounds area. I'm not a security expert, so I don't really know the details, but they filed a CVE for this and credited us in their iOS 10.3 security update. And here's a little video of some security bugs we found using the Graphics First project. So the first one is on the Samsung Galaxy S6 phone, quite an old phone now. This has an ARM Mali GPU.
I'm browsing the Bank of America enrollment page in what...
Let me just talk you through this and turn my volume off. I don't know whether muting my laptop will mute it from here. If it doesn't, I'll just let my old self talk. Okay, so yeah, this is Bank of America homepage. Now we're going to another tab using WebGL to render a shader. And that shader is not being rendered, but instead we're seeing garbled data from the other browser tab being rendered, right? And we were able to then capture that data and send it back to a remote server. So this was quite a serious security issue. This was a denial of service security issue where we could, on an AMD machine, run a shader in this looks like Edge or Internet Explorer, and yeah, it would just lead to a blue screen of death. So completely for the machine, a phishing attack could be used to get someone to visit a WebGL-enabled page, and their machine would die. This is a case with a Qualcomm GPU and an HTC phone sped up the video because it took a while, but we would visit this page, and after a while, the phone would become unresponsive and then suddenly reboot. So yeah, I won't show you them all, but we found a number of interesting security issues here. Some of them led to CVEs. The S6 one led to a Google bug bounty. This then led to us getting some funding from Google to specifically try to find security vulnerabilities using various testing techniques, and we didn't find any. So when we weren't trying to find them, we were just doing our compiler testing. We found quite a few security problems, and then when we thought, okay, if we were really going to try and find security problems, what would we do? And nothing we tried worked. It was quite amusing. I thanked myself that I'm not a security researcher. Okay. Then I'll just say a bit about some of the things we did. In addition to rolling this out to try to find bugs in the most critical GPU drivers from Google's perspective, we also used it to try and improve the reliability of the Android operating system with respect to graphics more generally. So to give you a bit of context, as I'm sure you know, the Android operating system comes from Google. Google lead the Android open source project. However, Google don't make that many actual devices. Google have their Pixel line of phones, but most Android devices are not made by Google. They're made by big players like LG and Samsung and Xiaomi and many, many of these OEMs, original equipment manufacturers. So there's this issue where if, my mum has got an Android phone, my mum's not a computer scientist, and it goes wrong, she'll just think Android's rubbish. She might think, if she knows that Google make Android, she'll think Google are rubbish. Whereas it might actually be that Samsung are rubbish or LG are rubbish, okay? So this problem may be nothing to do with Google or Android. It may be to do with third-party device drivers. But for the reputation of the Android brand and for Google's brand, it's pretty bad if these devices behave in an unreliable fashion. So to try to defend against this, Android have got something called the compatibility test suite. If any of you in this room wanted to make your own brand of Android devices, my understanding is you'd have to jump through a bunch of hoops to do it, and one of those hoops would be demonstrating that your device line passes the Android compatibility test suite. And in that test suite, there are tests for all kinds of things to do with the UI, to do with sound, and to do with graphics. And the idea of this compatibility test suite is essentially to try to stop bugs making it into end-user devices. But of course, the compatibility test suite has got gaps, and in practice, bugs are going to make it through the compatibility test suite into end-user devices. But the idea was to use graphics fuzz to try and close up some of those gaps, right? So synthesize more and more rigorous tests for graphics compilation, add them to the Android compatibility test suite to make it harder for bugs to make it through. And in particular, there's an issue that there's a long supply chain from a graphics driver at a company like ARM and the graphics driver deployed in your Samsung Galaxy S20 or 23 or whatever the latest number is phone. And the driver maker at the GPU company will make the driver, but then the original equipment manufacturer will patch that driver and then will deploy the patched version of the driver in their device. And there can be months and months and months and months or even years of delay between a bug being fixed in the driver and the fix actually making it into end-user devices. And sometimes the fix will never make it into end-user devices because it's always easier for an OEM to not take an update. It's cheaper and simpler for them not to take an update. But if they want to be conformant to the next version of Android, they need to pass the latest version of the Android compatibility test suite. So by finding bugs with graphics fuzz that affected today's devices, adding tests that expose those bugs to the compatibility test suite, we could eventually flush out those bugs from later devices, right? Because they wouldn't be able to gain conformance unless those bugs were fixed. So kind of, in my opinion, interesting social issue rather than a technical issue. All right, that's all I want to say about graphics fuzz, and I want to say a little bit about undefined behavior and being shot down by undefined behavior. So here's an example of a bug I reported to the Intel Mesa project, what I thought was a compiler bug, but it turned out just to be a bug related to undefined behavior, right? So the developer's written a very polite response indicating that my bug report was invalid. But you don't always get such a polite response from a compiler developer when you think you found a compiler bug and it just turns out to be undefined behavior. They're often pretty annoyed because people get this wrong all the time. I was well aware of undefined behavior when I filed this bug. I just hadn't spotted the undefined behavior in this particular example. So I want to go into undefined behavior in a bit more detail. I think it's a really interesting concept and something that many of you might take away from this talk, even if you're not particularly interested in compiler testing. To illustrate the example, I want to implement a function in C that does saturating addition. This is going to be a function that takes int values x and y, signed integers, and returns x plus y. But if x plus y would overflow, if it wouldn't be representable in the signed 32-bit integer range, then we'll get an extreme value. We'll get int max or int min, depending whether the value would overflow or underflow. So let's go ahead and try and implement this in VS Code. In saturating add then, we've got a main that is going to take two integers x and y from the command line, and it's going to print the result of adding them using this saturating add function. So a way we might do this, if we didn't know about undefined behavior, is something like the following. If x is greater than 0 and y is greater than 0, but also x plus y is less than 0, that would indicate that x and y were very large and we've added them together and we've got something negative, so we've overflowed. In that case, we'd want to return int max. Okay? And on the other hand, if x and y are both negative, but x plus y is positive, then that would mean that we had got underflow and we would want to return int min. And otherwise, we'd want to return x plus y. So if your view of computer arithmetic is that 2's complement is how you represent integers, signed integers, then this would be a perfectly legitimate way to implement saturating addition. But let's see what happens when we compile and run the program. So I'm going to use GCC 11 again to compile saturating add.c. And then I'm going to run the program, give it 3 and 5, and we get 8. Good. Give it some large number. We get twice that number. Let's add some zeros on. Good. Excellent, right? So when we add very large integers together, we get the int max value that you may be familiar with. Okay? And if I would make these be negative, then hopefully I'll get the int min value. Good. This all seems to be working correctly. Right? But now let's turn on optimizations. So let's say 02. And let me now add together these large numbers. So before we got int max. Add these together, and oh no, I get some negative number here. Okay? And now let me add these negative numbers together, and oh no, I get some positive number here. So it seems like this saturating addition is just not working at all. We're not getting the results we expected. And this is due to undefined behavior. Okay? So this is kind of just what I showed you. So without optimizations, we got the intended saturating addition behavior, but with optimizations, it just looks like wraparound behavior. It looks like our saturating addition just hasn't worked. We've got regular addition, which isn't what we wanted. Which of these results are correct? So without optimizations or with optimizations, which one of these answers is correct? What do you think? Both. Yeah? Or neither, or which is right? Yeah, both. Okay. So because the program has got undefined behavior, signed arithmetic overflow is an undefined behavior in C, then the program can do anything. It would be fine for the program to print gotcha or indeed exhibit any other behavior. In practice, the program won't print gotcha. It will do something rational, right? Rational from the compiler's perspective, and we'll have a look at that in a moment. The deal is that there are many things in C that are undefined behaviors, and signed integer arithmetic overflow is one of them. And there's a common wrong belief that undefined behavior is local, so that, for example, if you do z becomes equal to x plus y, you're going to get, basically, z is, if the sum of x plus y would be in the signed range, then x plus y, otherwise some non-deterministic value. Right? So you might think that you just get an arbitrary result if x plus y would overflow. But actually that's not true. The reality is more drastic. If you trigger undefined behavior on an execution, then the program has no semantics whatsoever for that execution. Any result at all is acceptable. And this is quite different from what many people think of as being the meaning of undefined behavior in practice. The C FAQ on undefined behavior makes it clear that anything at all can happen. it has this strange thing where it says the program may fail to compile. This is a bit of a misleading comment in my opinion, because typically undefined behavior is not something that can be detected statically, right? That saturating add we've got here, there's nothing in the code here that tells us that this will trigger undefined behavior. It just depends how we invoke the program, all right? But the more relevant part here is that you may, the program may execute incorrectly. I find that a bit misleading too, because it's not executing incorrectly, it's just not executing as you wanted it to, you the programmer who don't understand the programming language you're using, or it may fortuitously do exactly what the programmer intended. I think that's the key thing. Yep.
Maybe a naive question, but why do you not just define the behavior?
Yes, that's a good question. Well, the reason is that and I was going to include some slides on this, but I cut them for time. But there are certain behaviors that if you would define them, you would inhibit the kind of compiler optimizations that would be possible, or you would require specific compiler-generated code for particular architectures. To give you an example, overshifting has got different semantics on x86 versus MIPS, for example, right? Who cares about MIPS anymore? I don't know, but it does. Has different semantics on x86 versus MIPS. Back in the day, MIPS was very important. If you would mandate that overshifting would give you 0, then one or other of those architectures, I can't remember which, you'd have to issue some special instructions to make that be the case, whereas on the other one it would be free, right? And maybe offline I can show you some of the, there are some things to do with loop unrolling, for example, that wouldn't be possible if you had to ensure no overflow. A common misconception, and this comes from John Regeer's really excellent blog post on undefined behavior, is for people to have the following line of thinking. The x86 add instruction is used to implement C's signed add operation, and it has 2's complement behavior when the result overflows. I'm developing for x86, so I should be able to expect 2's complement semantics when 32-bit signed integers overflow. Well, this is not right, and it's like saying, somebody once told me that in basketball, you can't hold the ball and run. I got a basketball and tried it, and it worked just fine. He obviously didn't understand basketball, right? So just because you're working on one platform and you seem to be getting the results you expect, that doesn't mean that that's actually what you're gonna get for any compiler for this programming language or any compiler optimization settings. Okay, so the programming language has got rules, and if you break the rules, you can expect your programs to do weird things. The compiler is not misbehaving in compiling this program, because an optimizing compiler's job is to generate code that respects the language specification, to generate efficient code, okay? And in doing that, the compiler can assume your program doesn't have undefined behavior. The reason is that if your program does exhibit undefined behavior, then any semantics is acceptable for your program. So whatever the compiler does is fine, because it will lead to some semantics, and any semantics is okay. And if your program doesn't have undefined behavior, then the compiler is optimizing on the assumption that it doesn't, and if it doesn't, that assumption is valid, right? So if there is no undefined behavior, optimizing on the assumption of no undefined behavior is the right thing to do. And if there is undefined behavior, well, the compiler will generate some code, and that code will do something, and that's all you can rely on when there's undefined behavior in your program. So to illustrate this, let's imagine the compiler thinking about optimizing this program, this saturating add program. The compiler is going to assume the program doesn't exhibit undefined behavior, because if it does exhibit undefined behavior, then it matters not what code the compiler emits. Then the compiler could look at this first if guard and say, well, I know that x plus y doesn't overflow. That's a given, because overflow for signed numbers is an undefined behavior, and I'm assuming there are none of those. If x and y are both positive, and the result doesn't overflow, x plus y will also be positive. So I know that x plus y less than 0 is going to be false. And therefore, the whole condition is equivalent to false. And that's really good for an optimization point of view. So, replacing a complicated non-constant expression with a constant is a good thing to do. And by similar reasoning, the second condition is also equivalent to false. So the compiler can simplify this program to, if false, return int max, if false, return int min, return x plus y. Or better still, just return x plus y. Okay? And really, we have to credit the compiler here with full marks for doing the best it could at optimizing this program under the assumption of no undefined behavior. But ultimately, this program is just doing the regular addition that we were trying to get away from by implementing saturated addition, which is why with optimizations, we see the wraparound behavior in the end. So actually, nothing crazy going on here. There's a rational explanation for it. The compiler is smart enough to determine that these conditions are equivalent to false when you have undefined behavior freedom as an assumption and can make the program much simpler. So when you run the program at runtime on x86, you do have 2's complement semantics and you get wraparound behavior, which is what we tried to avoid when implementing saturating add. Okay. So why did I tell you about this? Well, because the last thing I want to talk about before I briefly comment on the empirical study I mentioned is test case reduction. If I find a compiler bug using some randomly generated or randomly mutated program, how useful would this program be as a bug report? If I turn up and say to GPU compiler developers, trust me, there's a bug in your GPU compiler, good luck figuring out the root cause of it. Compiler developers are not going to be happy. They probably don't believe me that this program triggers a bug. You know, maybe there's a problem with this program. Maybe it has undefined behavior. Even if they do believe me, what are they going to do? Are they going to hand execute this program? If the program crashes the compiler, fine. Crashes are fairly easy to root cause. But if the program just leads to a different result with this optimization setting versus that optimization setting, it's going to be really difficult to pin down the problem. So it's vital when you do any kind of serious randomized testing, but compiler testing in particular, to have test case reduction. If you've got a huge randomly generated program that triggers some sort of failure, this is not going to be actionable for developers. If you have a test case reducer that can give you a much smaller program that triggers the same problem, this is going to be something that developers can work with. It's going to really help them in understanding the bug and fixing it. But undefined behavior creates a real problem for test case reduction. Let's suppose we've got a huge randomly generated program, maybe it came from CSmith, and it's free from undefined behavior, and it triggers a failure. If we then hack away naively at that program with a test case reducer and get a small program, if in the process of hacking at the program we introduce undefined behavior, maybe we end up reading from data that's no longer initialized because we removed the initialization code, for example, then this program would be actionable, but actually, although it seems to trigger a failure, that failure may actually just be the result of undefined behavior, which may be perfectly acceptable. So a challenge in doing test case reduction is avoiding the introduction of undefined behavior during the test case reduction process. In the context of C compiler testing, there's a really great tool called CReduce, which is a complement to the CSmith program generator, but is also just a fantastic reducer in its own right for any kind of C or C++ test case reduction problem. It's also from John Regeer's group and also won a most influential paper at PLDI. I think this should actually say PLDI 2012, not 2013 though. How do these tools avoid undefined behavior? Well, CSmith avoids undefined behavior in generated programs by safe arithmetic wrappers. So for example, instead of generating a division expression directly, CSmith will always generate some call to a wrapper function, like safediv, that will check whether the denominator is 0. And if the denominator isn't 0, it will yield the division expression that was wanted. But if the denominator is 0, it will yield some well-defined result. In practice, it just yields the numerator of the expression. This way, you can generate programs that feature a safe version of division, a version of division that will never go wrong. If the denominator would be 0, it will just evaluate to the numerator. So this is a fairly blanket way of avoiding arithmetic undefined behavior. Yeah?
I just have a question about the notion of program being UB-free.
Yeah.
Does that mean that the program doesn't produce anything that is undefined under any input? Or
That's a good question. So the question was, is a program free from undefined behavior if there does not exist an input that would trigger undefined behavior? Or rather, is this defined on an input-by-input basis? It's defined on an input-by-input basis. In particular, if we look at this saturating addition program here, it's not true to say this program has undefined behavior. It's rather true to say this program would exhibit undefined behavior if you called the program with sufficiently large values of x and y. And it's very important, really, because otherwise any program that featured division anywhere in it would have undefined behavior because that division could, for some inputs, go wrong, right? But in practice, we say that an input triggers an undefined behavior rather than a program has undefined behavior. However, I often end up saying the program has undefined behavior, when really what I mean is when you executed this program on an input of interest, you would get undefined behavior. Does that make sense? Yeah, thanks. Okay, C-Smith also does some generation time pointer analysis. Having generated a function that's going to work with, say, a pointer to a pointer P and with a pointer Q, it ensures that this function is only going to be called with suitably valid pointer arguments that are going to refer to legitimate allocated regions of memory. How does C-reduce avoid undefined behavior when it's shrinking a program down? Well, it relies on external tools. You hook C-reduce up with a collection of your favorite lightweight analysis tools for C. These can be static analysis tools and or dynamic analysis tools, things like address sanitizer and undefined behavior sanitizer. And whenever C-reduce tries a candidate reduce program, it first runs it through this array of tools, and if any of them complain and say undefined behavior or possible undefined behavior, that candidate reduce program is discarded and another one is tried. And only when a program that has no sign, according to these tools, of undefined behavior is considered, does it actually get passed onto the oracle to see whether it still triggers a bug. This works out very well in practice for C and C++, where there's a rich ecosystem of tools for undefined behavior detection. But what if you've got a programming language where those tools just don't exist? Your language has undefined behavior, but those tools just don't exist. And this is very much the world I inhabit in GPU computing. GPU programming languages do have undefined behaviors. However, there is not a rich ecosystem of tools for detecting undefined behaviors in those languages. At PLDI 2021, we had a paper about the use of a different kind of test case reduction in the context of metamorphic testing, which I'll very briefly give you the gist of. Let's say you've used metamorphic testing to find a compiler bug by taking an original program P, transforming it many, many, many times to get a transform program, and finding a mismatch between these two programs. Well, rather than trying to actually reduce either the program P or the transform program, what we can do is we can apply test case reduction to the transformations. We can use what's called delta debugging to try and find the minimal sequence of transformations that you need to apply to P to get a bug triggering program P prime. So we might find, for example, that transformation number 82 and transformation number 531 are two transformations that suffice to cause the compiler bug of interest. All the other transformations turn out to be irrelevant, but these two are both needed. If we remove either one of them, the bug doesn't trigger, but these two transformations together cause the bug to trigger. And now, this pair of programs, P and P with these hopefully small transformations applied, they constitute a bug report we can file where we can say to the compiler developer, look, this very simple program P works just fine. If we consider this very similar program, P prime, that's obviously got the same semantics, because look, just these two small transformations have been applied, we get a different result, then that is actionable for the compiler developers, as long as P is relatively small in the first place and the transformations applied to it are not too drastic. So no need for undefined behavior detection tools here. What about differential testing? Can we support test case reduction for differential testing without undefined behavior detection tools? And we have a paper about this at PLDI 2023, which works well for relatively simple programming languages, like the graphics languages I've been interested in. So in the case of differential testing, we've generated a program, and we've ended up with a mismatch between the results of executing the results of compiling this program with two different compilers. And the problem with program reduction is that if we hack away at this program, make it smaller and smaller and smaller while preserving the mismatch, then what we might end up with is a very small program that is just garbage, right? This program, say, declares an integer x and then prints the result of x divided by x minus x. So this program is full of undefined behavior and is going to be no good, all right? The reducer introduced undefined behavior. And as I mentioned, C-Smith generates these nice, well-formed programs using protective layers. So there's a nasty, undefined program lurking inside a C-Smith program, and protective layers are used to make this into a nice program. Like I said, instead of generating direct divisions, it would generate wrapped divisions. and CSmith and CReduce hack away at a program, CReduce hacks away at a program with the help of all these tools I mentioned before, like Valgrind and Address Sanitizer. But if those tools don't exist, which is very much the case in, say, the OpenGL shading language or the Web GPU shading language, another language I'm increasingly getting interested in, then what are we going to do? How are we going to do meaningful differential testing for these languages if we don't have a sound way of reducing our programs? So our idea is called reconditioning. And the idea is that instead of the traditional setup where you have a generator that generates a well-defined program with these protective layers by construction, the idea is to have a generator that generates a program that may well have undefined behavior, and then add the protective layers via a separate step called reconditioning that will take the nasty, potentially ill-defined program and make it into a program that's sure to be well-defined. So what's the point of this? This doesn't make program generation or bug finding any easier. But what it does is it allows us to avoid undefined behavior during test case reduction. The idea would be we would generate program after program after program, and on generating each program, we would recondition it to get rid of undefined behavior and give it to the compilers under test. And if after a while we find a mismatch, we would then want to reduce this bug triggering program. And we could do that in the following way. We could apply reduction not to the UB-free recondition program, but to the nasty program without reconditioning. We could hack a piece off this program, but then we could recondition the remainder of the program so it doesn't have undefined behavior and ask, do we still trigger a compiler bug? If we do, we can hack another piece off and recondition that piece. And what I'm showing you here is that maybe the smaller program is 251 lines, and maybe it becomes 290 lines when we recondition it, because we have to add some infrastructure to avoid undefined behavior. So there's a price here, but the program is gradually getting smaller and smaller. And what we end up with is a small program that possibly does have undefined behavior, but when we recondition it, we get a slightly larger program, but still a small program, that doesn't have undefined behavior, that triggers the compiler bug, and this recondition program is what we would file to compiler developers as a bug report. So it means that we don't need any tools for detecting undefined behavior. All we need is this reconditioning tool for getting rid of undefined behaviors in a blanket way by, for example, doing the safe math wrappers that CSmith employed. And just to be clear, you don't want to do this for languages like C, where you've got undefined behavior detection tools, but it's useful for languages like the OpenGL shading language or the Web GPU shading language, where you have undefined behavior, but you don't have the corresponding tools to detect it efficiently. And it worked very well for these languages, leading to some fuzzing tools that found a whole load of bugs, and we were able to successfully reduce bug triggering programs thanks to reconditioning. Okay, I've only got a couple of minutes, so I'll just very briefly tell you that we always have this question of, do compiler bugs matter? Do fuzzer-found compiler bugs matter? You know, would anyone write that? Would a tool generate that? Oh, well, you never know, or a bug is a bug. People's attitudes vary widely on this. You know, I showed you this GPU compiler bug, and we could have an argument about whether this bug matters. Some time ago, Christian Kadar and I, together with our postdocs at the time, Chi and Michael, decided to have a go at investigating this empirically. Because, like I said, opinions in practice on compiler bugs really vary. So this is an anonymous reviewer of actually the first attempt at publishing our empirical study. They rejected the paper, basically saying, in my opinion, compiler bugs are extremely dangerous, period. I'm sorry if you were in the room, reviewer. Thus, regardless of the real-world impact of compiler bugs, I think techniques that can uncover and help fix them are extremely valuable. Why should we bother asking this question of, do fuzzer-found compiler bugs matter? So that's a kind of relatively purist point of view, a point of view of, actually, ultimately it's my point of view, it's a kind of formal methods person's point of view, right? We really just want to make software more reliable. Bugs are bugs, period. In contrast, this is not in response to our work, but a general remark we found on a blog post online. Someone saying, I would suggest that compiler developers stop responding to researchers working towards publishing papers on fuzzers. Responses from compiler maintainers is becoming a metric for measuring the performance of fuzzers, so responding just encourages the trolls. And this is absolutely true, by the way. There is an unhealthy culture in the fuzzing community of try and file as many bugs as possible. Find bugs, file them, file them, file them. Pressure developers to fix them. it's really bad. It's making a bad name for fuzzing. So responsible fuzzing, where you're careful about the bugs you report, you maybe even try and fix some of the bugs yourself, you don't just flood developers with bugs, it's a very real problem that we need to be careful about. What we did in this work was a large empirical study where we reintroduced numerous fixed bugs into GCC and LLVM. 27 bugs found by fuzzers, 10 bugs that were just reported in the wild by end users, and 8 bugs that were found via the Alive formal verification technique. And we assessed the impact of these bugs on 309 Debian packages spanning more than 10 million lines of C and C++ code. And what we were asking were things like, do we actually get to the point in the compiler responsible for this bug? Do the precondition for the bug to trigger, does it hold? If it does hold, do we end up with a different piece of object code? Like, did the bug make it into the object code? And if so, do any tests fail for this package? Do any tests in the test suite fail? So I won't go through the results of the study in any detail, but basically, we found that bugs affecting a mature compiler very rarely affect application reliability using these Debian packages as a proxy for applications. We assessed this via test suites and some manual inspection. And we found that the impact was no different depending on whether these bugs were fuzzer found or whether they were bugs that were reported by humans in the wild. So it was a very fun, time-consuming, somewhat inconclusive study that mainly seemed to say that it's not that clear that these compiler bugs had much impact at all, but it certainly didn't do what we were expecting of maybe saying, the fuzzer found ones, they never matter, but the user-reported ones are really critical. It really seemed to be the case that these Debian packages were pretty robust to these particular compiler bugs. All right, and finally, when you do compiler testing, you often get very useful byproducts. I mentioned improving the Android compatibility test suite by better conformance tests. This was mainly in the context of the Vulkan GPU programming model. You can get clearer language specifications because often when you think you found a compiler bug, it turns out you've actually just hit on a corner of the programming language that has ill-defined semantics. And when we were doing test case reduction using the pharmacy tool as an undefined behavior detection tool for C, we actually found a number of bugs in the pharmacy tool, and the pharmacy developers were very responsive to those bug reports and got those bugs fixed. So it can be a good way of improving the ecosystem all around. And over the last few years and in some ongoing projects, I'm interested in applying compiler-like testing techniques to a variety of domains. For example, testing program analyzers, finding bugs in hardware equivalence checking tools, analyzing the compilers for verified programming languages, where arguably it's critically important that compilers work well because you formally verified the source code, and if you've put all the effort into getting a formal guarantee, if that's undermined by a compiler bug, that could be pretty serious. And also using compiler testing-like techniques for API fuzzing rather than actual compiler fuzzing. Okay, it's been a pleasure talking to you. Thanks for the questions throughout, and if there's time, I'd be delighted to take any more now. Thank you. Yeah, so the question is, how do we come up with the transformations for metamorphic compiler testing? It's mainly a combination of two things. What hunches do we have based on our experience working with compilers of areas that might be difficult to compile? And what would be pretty easy to implement in the transformation framework? So for example, it's well known from the work from Zhendong Su's group on equivalence modular inputs testing, the control flow is often a problem for compiler testing. So one transformation that proved to be very effective was inserting dead breaks, things like in a loop, a false conditional that would break the loop or continue the loop or return from the function the loop's inside. So that fell into the category both of, we've got good reason to believe that complicated control flow may be a good way to tease out compiler bugs, and also those transformations are very easy to implement. Okay? Another thing that's well known is that often compiler bugs, and this is based on, I guess my experience of compiler testing, things to do with data structure layout can often be tricky for compilers, to do with things like padding, and that motivated transformations like packing data into vectors or structures. But what we haven't done is anything systematic, trying to say, well, if we do these sorts of transformations, we have any sort of guarantee that we've got uniform coverage of the language or of the compiler. we've been doing mainly black box testing of closed source graphics compilers, so it's unclear to me how we would get any kind of notion of being systematic there.
So I'm wondering if you can say something about fuzzing for problems not with the semantics, but with the, say, misoptimizations and things like that in the compiler. Whether you can say something about that.
Oh, fuzzing for things like missed optimizations? Yeah, well, the work that I'm aware of that's very... So yeah, first of all, random program generation is not a good fit for trying to find performance-related compiler bugs because you have no performance expectation for these programs. And even if you would do something like, say you had a randomly generated program and then you would do a semantic preserving mutation that would maybe speed up the program massively, it's not at all clear that that would indicate that, or slow down the program massively. It's not at all clear that that would indicate an optimization bug that anyone will want to act on because this might not help at all with real-world programs. The work that I know of that is really cool in this regard is from, I think it's from Zhendong Su's group at ETH Zurich, and it involves identifying... No, I can't. There is a very cool paper published a few years ago about finding missed optimization bugs that I can't remember off the top of my head, but it's a really clever technique. So if you're interested, I can point you towards that technique.
Yeah, thanks for the presentation. So I have a specific question. This example that you gave where refactoring exposed a bug, that means the example in the graphics shading, where you did a very simple refactoring and that exposed a bug.
Yeah.
So I think that's a very interesting, from a test program generation point of view, that's quite interesting because you are doing these semantics preserving transformations and yet somewhere down in the pipeline it is exposing the bug. So I'm curious, the debugging was done separately. It had nothing to do with the way you exposed the bug, right? You just reported that once you did the semantics preserving transformation, it caused a crash or something like that, and then the debugging was done by the developers separately. They somehow found it outside your pipeline.
Yeah, that's correct. So what happened was we took the original program. Our tool would have generated a variant shader that would have had thousands of transformations applied to it in all areas, maybe turned the shader from being 100 lines long to 10,000 lines long. This would have led to an image mismatch. Then our automated test case producer, that's based on that, it predated that PLDI work about shrinking the transformation sequence, but it's the thing that inspired that work, would get rid of as many transformations as it could while still preserving the mismatch. And in the end, the only transformation that remained was wrapping that return statement in the switch case. Okay? And then we would report that pair of shaders to the developers, the original one and the shader with this small change, and they would be able to confirm that, yes, indeed, the result completely changes. Then it's down to them. This was something, if I remember rightly, we reported it to AMD for their Windows device driver. That's a closed source device driver. The compile is part of the device driver. So I have no idea how they then went about debugging that.
This allows me to ask my question now. So did this debugging process, did they give any feedback which you can then distill to make your test program generation, that means the refactoring construction, a bit less random, so that you can gradually try to generate with higher probability these test programs which will expose crashes?
Yeah, that's a really nice question. For those in the side of the room, it's, did we get any feedback from the compiler debugging process that might inform the way we generate programs in the future? No, in the case of testing these commercial drivers, you just end up finding the problem's been fixed or maybe getting a notification on a ticket, this problem has been fixed in this release. However, with open source projects like the Intel Mesa 3D, the Mesa 3D graphics project that has an open source Intel backend, you do get to see the fixing patches. And I've often thought it would be pretty cool to study those fixing patches in some detail, which might inspire new kind of approaches. And the YARP-Gen, yet another random program generator project, which is another project from John Regier's group, is a collaboration with Intel compiler folks. And the idea there is to do what are called generation policies, where they have ways of trying to generate certain shapes of code fragments, and those are based on knowledge of how the LLVM compiler works internally. So the idea there is there's nothing automated about the construction of those policies, but they have crafted generation policies based on their compiler expertise so that they're trying to really hit the bits of the compiler they know might be worth thoroughly testing.
Okay, thank you very much.
You're welcome.
Last question from Olivier and then we go to the break.
Great talk, thank you very much. A quantitative question.
Yeah.
At the very beginning of your talk, you gave two bugs. One was the syntax bug,
Yeah.
and the semantics. And then you concentrated on the semantics bugs. But then you used program generators. So the quantitative question is, when you generate programs, how many syntax bugs does it reveal and how many semantic bugs does it reveal?
Yeah, good question. The question was, to what extent do we find syntax-related bugs versus semantic bugs? The thing that makes that hard to answer is that it's very difficult to deduplicate semantic bugs. If you have a bug that crashes the compiler or leads to the compiler rejecting programs it shouldn't reject, you typically can tell whether different programs are triggering different bugs because you get maybe a different stack trace from a crash or very different error messages from the front end. The problem with the miscompilation bugs is that you just have a program where you get different results from different compilers. Now, if you take another program where you get different results, well, they're different programs, so they should produce different results from each other. So this pair of result mismatches and that pair of result mismatches may be from the same underlying bug or from different underlying bugs. So it's actually very difficult to know, in this fuzzing campaign, have we found 5 distinct miscompilation bugs, or have we found 3,000 distinct miscompilation bugs? It's never going to be the latter. It's always going to be more like the former, right? But knowing how many distinct bugs you found is a very difficult thing to measure. So I don't have an answer to that. But I would say it's much easier to find bugs that crash the compiler than it is to find miscompilation bugs. So I haven't measured it formally, but my feeling from the various projects I've done is you quite often find, this weird input crashes the compiler, so what? Whereas it's much rarer and more exciting to find this well-formed input that really causes, the wrong result to be computed by the compiled program.
So the very first bug that you described was very troublesome because you added code that ultimately was dead, and then the optimizing compiler would analyze that code and then generate. And that's contrarian with respect to your chopping of pieces of code. Because that means that you take a bigger program which has a bug, you chop off the part that is dead, and then it has no bugs.
Yeah, but the thing is that we didn't synthesize that program that found the bug. We synthesized a much, 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 much bigger program than that. The test case reducer did manage to chop away everything, and logically it should have been able to chop away that function too, but it couldn't, because when it would have tried to do so, it would have tried to even, you might have noticed some of the variables were static. If you remove static from those variables, the bug goes away, right? So that program was really minimized. I then further minimized it by hand to try and help the LLVM developers debug it. So really, the idea of test case reduction isn't, logically, this should be able to be removed without affecting that. It's more, if we remove this, does the bug go away? Oh no, if not, we need to put it back then. And there's no logic to these bugs. So indeed, it very much is a kind of constraint-based reduction where the constraint is the bug should still trigger.
All right, sure there are more questions, but we have lunch waiting outside, so let's thank Ali again.